Okay, so we'll start our discussions on where we left off in the previous class. And we were actually discussing this MOSFET amplifier cheat sheet that you can use for analyzing any kind of amplifier-based circuits which involves MOSFETs. And we have looked into common source amplifiers, we have looked into common source with source degeneration, we have looked into all the derivations of the common source stages with and without source degeneration. We have looked into common drain, we have looked into common gate. So those are the different topologies that we have looked into. And we also started looking into diode connected MOSFET. And we have seen that for a diode connected MOSFET, even though you are looking from the drain, you'll see a resistance of 1 upon Gm. So previously what we have shown is that, let's go back to, over here, that if you have a MOSFET and if you're looking at the drain terminal of that MOSFET, the resistance that you see will be equal to RO, assuming that RO is infinite. So you see a resistance that is infinitely large if you're looking into the drain terminal. But that is assuming that, okay, you are biasing the gate using a separate voltage. You are not connecting the gate and the drain together. Similarly, when you are looking into the source of a MOSFET, you see a resistance of 1 upon Gm, right? But the only specific scenario that we'll encounter in the analysis to follow is that for diode connected MOSFET, when you have the gate and drain connected together, the resistance looking into the drain will be 1 upon Gm. And of course, the resistance looking into the source will also be 1 upon Gm. For this particular scenario, the resistance looking into drain is 1 upon Gm, resistance looking into source is also 1 upon Gm. And we have done the proofs and everything, so I'll not go over it once again. Then we were looking into a few different examples, and this is one specific example that we had looked into in the previous lecture. That if you see this kind of a structure, let's say you already know what this structure means. It's a common source stage because you're applying your input at the gate, your source is grounded, and your drain is the point from where you're taking the output. So of course, this is a common source amplifier. But what's new is that instead of connecting a resistance at the drain of the common source MOSFET, you're connecting a diode connected stage. And that you can do because you already know that what is the resistance looking into the drain of the diode connected stage, that is 1 upon Gm2. Right? So if the overall, like earlier what we have shown is that the gain of the common source stage is minus Gm times RD, where RD is the resistance connected at the drain of the common source stage. So for this particular MOSFET for M1 transistor, if there was a resistance that was connected at the drain, that would have been RD. Now, in this case, what is RD? RD is equal to 1 upon Gm2 because the resistance that you see looking up is 1 upon Gm2. So instead of RD, you just use 1 upon Gm2 and that will give you the equation for gain. And the equation for gain in this case will be minus Gm1 divided by Gm2. That's just because the resistance connected at the drain of the common source amplifier of the common source transistor is equal to 1 upon Gm2. And that you can simplify a little bit by representing Gm as square root of twice K times ID. Now, assuming, of course, the ID current will be equal through both of these transistors. If there is a current flowing in this path, which is equal to ID1 or ID2, and this current is ID1, of course, ID1 has to be equal to ID2 because that's what KCL tells you, that you cannot create current, you cannot destroy current eventually, right? So ID1 will be equal to ID2. And in that case, this ratio will be just minus of square root of K1 divided by K2. And then again, you can represent K as mu times COX times W over L. And if you make the correct approximation, eventually you will end up with a gain that is a constant times square root of W1 over W2, where W1 and W2 are the widths of the MOSFET. W1 is the width of the MOSFET 1, W2 is the width of the MOSFET 2 or MOSFET M2. Okay. Now, for this case, because you cannot really, it's not physically that much realizable if one transistor is, let's say, 1,000,000 times larger than the other. That's not something you'll see in a design. Usually the transistors are almost equal size, or maybe one transistor could be 5 times larger than the other, or maybe 20 times larger than the other. But it's very rare to see a transistor which is 100 times larger than the other transistors in the design. And that is because it makes it much harder to connect, let's say, different. So, for example, this is one transistor, this is the other transistor. Let's just assume this transistor is 100 times bigger than the other. Then making all these connections to the gate and the sources and the drains, connecting this drain and the other drain together becomes much more troublesome. If one transistor is much larger in length than and width than the other. So that's why it's not a very common practice that you see that one transistor is 1,000,000 times larger than the other. Usually one transistor could be, let's say, 20 times larger than the other or 50 times larger than the other. But it's very rare to see anything beyond that. And if that is the case, your W1 and also other things that come into the picture when one transistor is too big is the parasitic capacitances of that transistor. And if the parasitic capacitances are very large, then you'll see that many of our approximations, the analysis that we had done in the past will not be consistent. That will not be true because there could be additional current paths through those parasitic capacitances. There could be leakages through those parasitic capacitances, and that will make your life very hard. So that's why it's not a good practice to have one transistor much larger than the other. But what you can have is, let's say, one transistor 25 times larger than the other. Then square root of this 25 will be 5. So that's why usually for a direct connected load, the gain could be, let's say, as large as 5. But as soon as you want to make it 20, you have to have one transistor 400 times larger than the other. Just ignoring this constant term for a moment, one transistor needs to be 400 times larger if you need to make this gain equal to 20. So using the direct connected structure, you do not usually get a very good amount of gain. But the advantage that it gives you is that you do not need to place a resistor. So how do you actually create a resistance? You will either have to connect an external resistance at this point of the MOSFET, right? So remember that what we had learned earlier, the structure looks something like this, that you are applying your input at the gate over here, and this is your RD resistance. So this RD resistance could be something that is external. So you have a MOSFET which is micrometers in width and length, but then outside you have a resistance that is a few centimeters in length and width and so on. That is one possibility, and that works. I mean, it's not that it does not work, but if you want to make everything on chip, the idea behind designing circuits with MOSFET is that MOSFETs can be very small, and you can pack a lot of these MOSFETs together in a tiny area. And that's what some of you may know about Moore's law, like what Gordon Moore, at the time he was in Intel in 1965, what he has said at that time is that every year or every 2 years, you'll see that the number of transistors in a certain area will keep on doubling. Right? That was just a prediction, but that came out to be true for the next 30 to 40 years. That every 2 to 3 years, people were able to make the technology much better, much more improved, so that you can pack more and more transistors within a given area. And that's always the benefit, because today, within a 1 millimeter by 1 millimeter chip, you can pack millions of transistors. So if one transistor can create an amplifier, or 2 transistors can create an amplifier, imagine what millions of transistors can do, right? And that's the advantage of Moore's law. That's the advantage of scaling. That's the advantage of integration of many transistors within a small area. Now, of course, if you want to place an external component over there, then some of those advantages go away, because you are already putting a centimeter scale device along with the millions of micrometer scale transistors that you have. So instead, what people had looked into is that how to implement this resistor within a chip as well. So within a particular integrated circuit, can you implement a resistor? And that is possible to do. Some of you already may know about this, but the polysilicon that you use for gates. So if you have taken a devices class, you know what polysilicon will mean. It's just amorphous silicon that can be used at the gate of the transistor, and that works somewhat like a metal. It's much more conductive than a metal. And when you have conductance, 1 upon conductance becomes your resistance. So using the amorphous silicon or polysilicon, you can create these these resistances on chip as well. But then again, the challenge there is that on-chip resistances, those on-chip resistances take a lot of area. They consume a lot of area. Again, I got a Moore predicted in 1965 that you have to reduce area if you are going to pack more and more transistors within the small space that you have. So if you're using something that takes up a lot of area, that defeats the purpose. So instead of using this resistance, you can use the MOSFET, which is again a very tiny structure. Instead of this resistance, which could be hundreds of micrometer long or wide, you can use a transistor, which could be, let's say, just a micrometer long or micrometer wide. So that's the advantage of not using the resistance and using a MOSFET over here. Okay. Now, what we have seen is that even if you are using this MOSFET as a resistance, you are using that MOSFET as a replacement of 1 upon GM2 resistance, like that value of resistance, which could be 1 upon GM, right? Because you are looking at a drain of the direct connected MOSFET. Instead, what you can do, you can have a structure which is called a current source load. The previous one was called a diode connected load because your load resistance was a diode connected MOSFET. And there we saw that the gain would be usually low in the range of 5 because this ratio of transistors will not be very large. Now, in the current source load, the advantage is that as you are looking into the drain of this N2 transistor, how much resistance do you see? Do you see 1 upon GM or do you see RO? In this case, you see RO, right? Because this is not diode connected anymore. So the resistance that you see here is RO. And usually the RO of the transistor is much, much higher than 1 upon GM of the transistor. This is something you may have found when you solve your homework number 4 or homework number 5, that the GM of the transistor could be, let's say, a few millisiemens. Even if it is 10 millisiemens, or let's say even if it is 1 millisiemens. So let's say GM is equal to, I'm just taking some numbers, this may not be true at all for all applications. If GM is equal to 1 millisiemens, that is 1 milliampere divided by volt, right? So this is something you may have seen in your homework number 4 or even in the exam question, that the GM was a few millisiemens in most cases. So what is 1 upon GM? What is 1 upon 1 milli? That is 1000, right? 1K. So 1 upon GM would be 1K, 1 kilo. On the other hand, RO of a transistor, the intrinsic resistance of a transistor is usually in the range of hundreds of kilo. And let's just call it 100 kilo for now, for the sake of simplicity. So as you see that RO is at least 100 times larger than your 1 upon GM. So if your gain is determined by this, in this case, it will be determined by minus of GM1 times the resistance that you see looking into the drain of this M2 transistor, right? Or resistance that is connected to the drain of this M1 transistor. Now, in this case, you have to, because you are considering RO, and RO is much, much larger than 1 upon GM. In the previous case, it was also true. There was an RO of this M1 transistor as well, which we can call as RO1. And the resistance looking up was 1 upon GM2. Now, 1 upon GM2 was much, much smaller than RO1, right? 1 upon GM2 would be much, much smaller than RO1. And that is the reason why you only considered the resistance looking up. Remember that when you talk about this minus GM times RD, this equation, the exact form of this equation would be minus GM times RO parallel to RD. Right? It's not just GM times RD. If you think about the small signal model, there was this RO resistance of the transistor. Again, if I can go back over here, the RO resistance of the transistor is something intrinsic to the transistor between the drain and the source, and the RD comes in parallel to that resistance, right? So effectively, it's RO in parallel with RD. If RD is much, much smaller than RO, then you can ignore RO because these two resistances are there and one resistance is much larger than the other. You can ignore that larger resistance. That's what we did when we talked about this particular equation, that okay, your gain is minus GM times RO in parallel with RD. But if RO is much, much larger than RD, then it becomes minus GM times RD. That's what happened in this case. That your 1 upon GM2, that's what your RD was. The value of RD was 1 upon GM2, looking up at the drain of the diode connected M2 transistor. So 1 upon GM2 was much, much lower than RO1, and that's why your gain became almost equal to minus GM1 divided by GM2. But in reality, you should have considered this 1 upon GM2 in parallel with R1 if you wanted to be exact, but that will not change your analysis, or that will not change the values in your design. But in this case, what is happening is that looking up at this point, you will see RO of the M2 transistor, but at the same time, in this direction, you have the RO of the M1 transistor. And these two ROs are coming in parallel because this is the point where at which you are taking the output. Looking up, you see RO2 connected between the source and the drain, or drain of the source of this PMOS transistor, and this source is connected to an AC ground. Looking down, you see RO1, and the source of the NMOS transistor is also connected to the AC ground. So RO1 and RO2 are in parallel actually. If you just draw the small signal model, it will be very clear to you that why RO1 and RO2 are in parallel. And you can just draw it from here. Like you don't even need to draw the small signal model. Where is this RO2? RO2 is in between the drain and the source of the M2 transistor. RO1 is in between the drain and the source of the M1 transistor. Right? The drains are connected together. That means one terminal of these two resistances are already common. What is happening to the other terminal? For example, this terminal is connected to VDD, which is an AC ground. This terminal is connected to original ground, which is also an AC ground. So that's why the two terminals of both the resistances are connected together, which means the resistances are indeed in parallel. So it's kind of like this, where this is your output point, the drain. One of these is AC ground, one of these is a VDD, and the other one is a actual ground. So because VDD and ground are both AC grounds, you can say that these 2 points are connected together as well, which that means that R1 and R2 comes in parallel. So in this case, your gain will be, because you are applying your input at the M1 transistor, it will be GM of the M1 transistor multiplied with R1 in parallel with R2, that's your load. Now, of course, RO is much larger than 1 upon GM. So RO1 in parallel with RO2, that is basically, let's say, 200 kilo ohm resistances in parallel, that will still be 50 kilo ohms. So 1 upon GM was 1 kilo ohm. So in this case, you can get a gain which is, let's say, 50 times higher than the previous scenario. So if you want more gain, use a current source load. Don't use the direct connected load. Direct connected load can give you a gain of, let's say, 5, 7, maybe at max of 10. But if you want a gain of much more than that, use a current source load. This is just an example that if your GM1 is 200 microampere per volt, RO1 is 100 kilo ohm, GM2 is 40 microampere per volt, and RO2 is 200 kilo ohm. With direct connected load, the gain will be the ratio of the GMs. The ratio of GM1 over GM2 is just -5 if you had a direct connected load. If you have current source load, the gain will be minus GM1 times the parallel combination of the 100 kilo ohm and 200 kilo ohm RO. And the parallel combination of 100 and 200 will be 67 kilo ohms or so. And in that case, you'll get a gain of about 13.4, which is larger than the previous scenario, which had a gain of 5. Any questions? Yeah.
So when you were doing op-amps, the idea of like the product of the gain and the bandwidth,
right,
having to remain constant. So like if you maximize your gain, you minimize
your bandwidth reduces. Okay.
Does that also apply to the?
Great question. Great question. Yes. So what determines your bandwidth? So for example, I mean, it's a little bit of segue of what we are discussing right now, but because this is a great question, I'll probably try to answer it now rather than keeping it for later. So what determines your bandwidth in this case? And you know that bandwidth is nothing but a RC time constant. Any kind of bandwidth is a RC time constant eventually. So what is the RC time constant that you have here at the output side? The RC time constant you have is there would always be a parasitic capacitance from this point to ground, because any point in a design will have some capacitance to ground. If it is a physical device, it will have capacitance from any point to any other point. And it doesn't need to be a device. Even I have a capacitance from my body to the ground. Every one of you have a capacitance from your body to the ground, and so on. Okay. So there would always be a parasitic capacitance from any point to the ground. So at this point, you have a parasitic amount of capacitance, let's call that C power or C parasitics. What is the resistance? The resistance is the same resistance that you just calculated. R01 is parallel with R02. That's the resistance you see at the drain. So the resistance looking down is R01, resistance looking up is R02. The parallel combination of those two is the effective resistance at the output. So what is your RC time constant? Your RC time constant is basically R01 in parallel with R02 times C parasitics. So R01 parallel with R02 multiplied with C parasitics. Because your R1 parallel to R02 is large, this RC value is also large. If the RC time constant is large, bandwidth, which is corresponding to an inverse of your RC time constant, will be small. So even though you have a higher gain, your bandwidth will be small. On the other hand, think about the diode connected load. There, you had the same scenario that, okay, let me remove this first. So in that case, again, you have a C parasitics over here. Now, this C parasitic could be different from the other circuit because the sizes of the MOSFETs could be different, right? But assume that the sizes of the MOSFETs are exactly the same. It's not different at all. Let's say the size of the M1 and M2 transistor in this circuit is same as the size or the aspect ratio of the M1 and M2 transistor in this circuit. Let's just assume that the W's are equal, the L are equal, and everything is equal. Then the parasitic capacitance will be equal for both cases. But what is the resistance at this point now? Resistance looking down is R1, resistance looking up is 1 upon GM2. So it's 1 upon GM2 in parallel with R1 multiplied with C parasitic. That's the RC time constant that you have here. Now, of course, 1 upon GM2 is much smaller than R01. So this will be almost equal to 1 upon GM2 multiplied with C parasitics. So that means you'll have a small RC time constant. If your RC time constant is small, your bandwidth, which is an inverse of the RC time constant, will be larger. So in this case, your gain is small, but bandwidth is large. In the other case, your gain is large, but the bandwidth will be small. So that's a great question. That the same trade-off that we saw for op amps. Now we know why that happens. Right? This is an explanation that if this circuit is inside your op amp, this already gives you the reason why you will see as you're increasing the gain, why would your bandwidth reduce, and if you're reducing the gain, why would your bandwidth increase? So that's a possible reason if this circuit is inside the op amp. More questions? I'll take his first. Yeah. Again, that's a good question. So the noise, so it's not the fact that the devices are getting small and you have more noise because of that. It's not that. Noise will affect you when your signal is small, because eventually all you look for is the signal to noise ratio. If your signal is higher than your noise, you can always detect your signal. So signal to noise ratio is something that you want in any kind of communication, or if you want to do any kind of DSP, digital signal processing. All you look for is a high SNR, high signal to noise ratio. Now, where your point becomes relevant is that as you are making the devices smaller and smaller, if you are not able to get enough gain out of these devices because of multiple non-idealities, then it could be possible that your signal will become smaller and smaller. And then your noise will start happening. So, of course, you have to take into keep this into consideration that your SNR does not degrade too much. And that's why there is a concept of low noise amplifiers. We are not learning low noise amplifiers right now, but if you think about RF system, so let's say radio frequency, let's say you're trying to communicate with the phone, then the signal that this phone receives is very small. It's most of the times even in nanovolts or so, right? Nanovolts. Now, if you think about power, it could be nanowatts or picowatts. So that's a very small amount of signal. Your noise has to be smaller than that so that you are effectively able to detect the signal over the noise. So that's why there is a concept of low noise amplifiers, which you learn if you're taking any RFIC course, radio frequency circuit design, IC design course. This is just a very basic primer to amplifiers. So we are not going to discuss LNAs right now, but that's a great question that eventually the amplifiers will have to take care of noise as you are dealing with smaller and smaller signals. One more question. Yeah. No, because remember that for diode connection, you have to connect the drain to the gate. If you connect source to the gate, I mean, if you just switch this N2 to an NMOS, so what you are saying is that I'll have this and still have this kind of a connection? Or, okay, you want to reverse the gate to drain as well. Okay. But you want to replace the into the PMOS with an NMOS. Yes, because then you are looking at the source of the NMOS, and at the source of the NMOS you will see GM, right? So what you are saying is that you replace this M2 transistor with, let's say, an M3 transistor that looks like this, right? So you replace M2 with M3, and M3 will be an NMOS that looks like this. So looking up at this point, you'll see the source of the M3 transistor in that case, and the source of the M3 transistor will be 1 upon GM3. That's the resistance you'll see at the source of the M3 transistor. So it will be GM1 divided by GM3 eventually. All right. So that's what, yes. And one other thing that we haven't discussed till now, that why is it called a current source loop? So you have this as a common source stage, but on top you have this N2 transistor where the gate and drain are not connected together, but you're connecting a bias voltage to the gate. Remember that how does it look like? So whenever you have a transistor in saturation and you're applying a gate voltage to it, you are applying a particular VGS so that this transistor is in saturation. And remember that what is the property of the transistor when it is in saturation? It will provide a fixed amount of current. So a transistor in saturation works as a current source, right? And if you don't consider the non-idealities, if you don't consider the lambda for a moment, a transistor in saturation works as a fixed current source. So how you can represent this as is, maybe it's not drawn over here, but I'll just draw it on the left hand side, that you have your VDD, then you have a current source. So let me just directly draw a current source over here, and then you have your M1 transistor, and you're applying your input at the gate of the M1 transistor. So this is what you have, that at the drain you're connecting a current source, and that's why it's called a current source loop. When you are using this transistor with a particular bias voltage of dB, you are actually creating a current source as the load of this M1 transistor. Now, of course, this current source is not ideal, right? The current source has a parallel resistance to it. And what is the value of that parallel resistance? That's the RO of the M2 transistor. So the RO of the M2 transistor is in parallel with the current source. And when you think about AC analysis, all you care about is the AC quantity. So if this is a current source is a DC current value. You don't consider DC quantities when you are doing an AC analysis. And that's why eventually when you want to do the AC analysis, your circuit reduces to just that you have your M1 transistor, you have your input voltage over here, and at the drain of the M1 transistor, you have the RO2 of the input transistor. Because this is a DC quantity. You don't need to consider the DC quantity when you are doing the AC analysis. You just need to use the resistance, which is the AC resistance connected in parallel to this DC quantity, and that AC resistance will be the load or part of the load of your circuit. And that's why it's called a current source load. All right. Now you can have a variant of the current source load where you can also apply the input signal to the gate of the load device. Let's say you have already biased the M1 and M2 transistor by some means. Let's not go into the details of biasing the M1 and M2 transistor. We'll discuss that in a moment. But for now, let's just assume that somehow you have biased. Somehow you have made sure that M1 and M2 transistors are both biased in saturation. Because if you don't bias in saturation, you'll not be able to use the equations that we have been learning till now. Those equations are only valid for saturation, right? And if you have biased those transistors in saturation, Then let's just assume that you are applying the input voltage at the gates of both the M1 transistor and M2 transistor. Right? So this is a special case of the previous scenario. Now you have two common source stages. One common source is here, and the other common source is there. Right? Both are common source because the sources are AC ground. The source of the PMOS is AC ground. The source of the NMOS is AC ground. And at the gate, you're applying the signal. At the drain, you're taking the output. So it's kind of like a superposition of the two common sources that you see over here. And if you can superposition, if you can use superposition theory, you know that you can increase the amount of signal at the output side. And that's what happens here, that here the GMs get added together. It's a superposition. Your GM, which is basically the current eventually that you see, the AC current that you see at the loads, will be a superposition of the currents. It means that the currents will get added, and that means the GMs will get added. The transconductance will get added. And the ROs definitely will come in parallel with each other as the previous scenario. So this will be the gain when you are doing a active load. So this is called active load because the load is not passive. In the previous cases, the load was passive. It was just working as a passive resistance. Here, the load is something that gives you an additional amount of GM as well. It gives you some active amount of gain. It is actively contributing in increasing the gain. That's why it's called an active load. And in this case, the overall gain is again GM times RO, but the value of GM, this is basically your capital GM, and capital GM is the addition of these GM1 and GM2. Okay. So in this case also you can get even more gain, because in the previous case you had GM1 multiplied with RO1 parallel with RO2. That was the current source load. Now you are almost doubling it, assuming that the GMs of M1 and M2 are equal, you are doubling the gain even more. Right? So this is another way to increase the gain to a much larger value. All right. What if you want even more gain? So this is something that again, it's a much more advanced concept and usually taught in graduate classes. But I'll just give you a glimpse of what if you want even more gain. Then you can use something called a cascode amplifier for a very high amount of gain. What this cascode amplifier is doing is that if you see this structure, that you have a common source stage with a load that is provided by these two transistor structure, and you're taking the output from here. You're not taking the output at the drain of the first transistor. You're not taking the output over here. You're taking the output at this point. So what that means is that this common source stage is creating a current corresponding to this input voltage. So at this point, you create a current that is GM times VGS of the M1 transistor. So GM1 times Vin is the current that you'll see at this node. Right? Now, then if you just ignore whatever is happening here below this line, let's ignore whatever is happening below this line. What you have is a current that is applied at the source of this M2 stage, and then here you're taking the output at the drain of the M2 stage, whereas this M3 is just working as a current source stage. So looking up, you'll just see a resistance of RO3 in this case. Okay. So this works as a what? It works as a common gate stage. You know, for a common gate, the input is applied at the source. The gate is an AC ground. In this case, this is an AC ground. The output is taken at the drain. So you have a common source stage to convert the input to a current, and then you are using that current as an input to your common gate stage. So this is kind of having two stages cascaded together, or this is called a cascode amplifier, not a cascaded amplifier. So this is different from cascade or cascaded amplifiers, where we have talked about this, that okay, you have one amplifier followed by a second amplifier. So let's say this is A1 and this is A2, and the overall gain will be A1 multiplied with A2. So this is a very similar concept, that you have one amplifier over here and another amplifier over here, and you're just multiplying the effects of those two amplifiers. But what is the difference between cascade and cascode? The difference is that when you have cascaded amplifiers, this amplifier draws a particular amount of current. Let's say it draws a 1 milliampere current. This amplifier also draws 1 milliampere current. Whereas in this case, because the amplifiers are stacked together, the 1 milliampere that will flow through this amplifier will be the same 1 milliampere that flows through this amplifier. So by using a lower amount of current, you can get the higher amount of gain. So that's the advantage of cascode over cascade. And what you have is basically a common source stage followed by a common gate stage. Eventually, the gain that you'll see in this case, again, you can do a small signal analysis. And again, as I said, that this is a much more advanced concept, so don't worry about it right now. This is just for you to know that this exists, and this is something that you can use if you want even higher amount of gain. Eventually, the gain of this system becomes a multiplication of the GM1 RO1. So that's the GM and RO of the M1 state, multiplied with GM2 RO2, that's the GM and RO2 RO of the second state. So it's kind of like a multiplication of GM RO of one stage multiplied by GM RO of the second stage. And that gives you a very high amount of gain. So cascode amplifier is something that you might use if you want a very, very high amount of gain. All right. So that brings us to the end of the summary of the MOSFET discussion. Any questions over here? If not, I'll discuss a little bit about homework 6 and how to solve the homework 6 problem easily. Now, of course, the first problem is something where you're given a glimpse of what can happen if you could start considering the parasitic capacitances at every node. And I talked about it a little bit in the previous lecture that for this MOSFET, what you're asked to find out is the input impedance. Now, if this MOSFET was ideal, the input impedance would be infinite because there would be no current going into the gate of the MOSFET. But now what we are doing is that we're giving a non-ideal model of this MOSFET. It's not a full non-ideal model. It's just that I'm introducing one single non-ideality. That's the gate to source capacitance, parasitic capacitance. So there will be a parasitic capacitance from gate to source, and through that parasitic capacitance, there can be some amount of current flow. Which means if there is some amount of current flow, that will mean that the input impedance will not be infinite, it will be a finite value. So you can use the same concept of finding input or output resistances, that same as finding Thevenin resistances. So nothing fancy, nothing different from what you have done before. It's just that you have to consider this additional current path that can, through which currents can flow. So just draw the small signal model of the amplifier, but consider this CGS capacitance and then solve for KCL and KVL. That would help you in finding out the input impedance of this MOSFET. Okay, and it will not be infinite, it will be a finite value eventually. The second part is something I wanted to discuss in a little bit more detail. So you see a much more complex circuit than whatever you have seen before. There are some parameters that are given that will help you to simplify things. That it is given that R1, R2, R3, 4, and 5 all are equal to infinity. That means that all the output resistances are very high. There is no channel length modulation, and you don't need to worry about those output resistances. It's also given all the GMs are equal and they are equal to GM. And it is also given the R1 and R2 and R3, these resistances that you see in the circuit, that is equal to 1 upon GM. So eventually that will simplify your design a little bit more. And all of these are N-channel MOSFET. So now you're asked to find out what is the overall gain of the system, or you can find out the output voltage as a function of the input current. Right? So this input is a small signal current. The input is a small signal current. This current source is used to bias this transistor. Okay. And you're asked to find out what is the output voltage, AC small signal output voltage as a function of the AC small signal input current. Now, how to solve these kind of problems? Again, as I said in the previous lecture, the easiest way to solve these kind of problems or these kind of circuits is to do a divide and conquer. So first, identify what are the different components of this system, what you already know. So you already know about all the different components in this system. There is nothing new over here. For example, if you just look into the first stage, what is this stage called? Where you provide your input to the source, your gate is grounded, and you take your output from the drain. It will be a common gate because the gate is grounded, right? So it's a common gate configuration. Common drain is a source follower, right? Common drain, in common drain, your drain is the common terminal. Here the drain is not the common terminal, your drain is the output terminal. So you have to identify what is the input terminal, what is the output terminal, and the third terminal will be the common terminal. If your input is source, output is drain, only one terminal remains. That's the gate. So the gate is the common terminal. So it will be a common gate topology. So first you identify the topology that, okay, this is the common gate. Now for the common gate, what is the I mean, you can go back to the cheat sheet. It's basically the common gate will be very similar to your common source, but the polarities will be reversed. That means you'll have a positive gain instead of negative gain. So let me see if I can find the common gate topology over here. This is common drain. Yeah, this is common gate. Where you apply your input to the source, your gate is grounded, and your output is from the drain. And for this, everything is same as common source. Now, if you have the source regeneration resistance, it will be common source with source regeneration, except for the sign. So let's go back to the common source case. And without the source regeneration, you will have capital GM as GM and R out as, let's say, RT, because the RO is infinity. It's given in the problem. So R out will be equal to RT, whatever resistance is connected at the gate. So GM times RT will give you the gain of the common gate stage. Now go back to the problem once again. So this is the common gate stage. GM of the M1 transistor multiplied with whatever resistance is connected at the drain will be the gain of this stage. Okay. But remember that gain, GM times RT, that's a voltage gain. In this case, what you are trying to find out is eventually find a voltage divided by a current. Right? So your input is a current in this case. Right? And if your input current is this, the same current will flow through the drain terminal as well. The same current will flow through the drain terminal as well, because looking down, you'll see a DC bias current, a current source. And the resistance of a current source is how much? It's infinity. So looking down, you'll see an infinite current, infinite resistance. So all this input current is actually flowing through the transistor and going in the upward direction. No current will go in the downward direction. Even though you see a branching over here, no current will go in the downward direction because the resistance looking down is infinite. The resistance of a current source is infinite. All of you hopefully know that, right? Now, resistance looking up is basically the resistance of this M1 transistor, which is 1 upon GM, but that's fine. We are not looking into that resistance right now. What you are interested in seeing is that what is the voltage at this output. You know the current is exactly same as IE. The voltage will be that current multiplied with the resistance that you see at the drain. What is the resistance that you see at the drain? You see R1 over here. But then there is a path going towards right-hand side. That right-hand side path will see the gate of this M2 transistor, and at the gate you see infinite resistance. So you do not need to consider this path that goes to the gate of the M2 transistor. However, there is another path that goes here, that goes to the source of the N3 transistor. Now at the source of the N3 NMOS transistor, what is the resistance that you'll see? 1 upon GM. It's a source terminal, NMOS, you'll see 1 upon GM. So here, at the drain terminal of M1, you basically have R1 in parallel with 1 upon GM of M3. And that's it. You know the resistance, you already knew the current at the drain terminal, you'll know the voltage at this drain terminal. So voltage at this terminal will be I in multiplied with R1 in parallel with 1 upon GM3. That will be the value of voltage at this terminal. I in, because all the current is going up, no current can go down through the current source. I in multiplied with R1 in parallel with M3, 1 upon GM3 will give you the voltage at this terminal. that voltage is going to this source follower. So the same voltage will be available at the gate because source follower just has a gain of equal to 1, right? So if it is, because this is ideal scenario, you'll see a gain of exactly equal to 1 for the source follower. So that same voltage is going to the gate of this M4 transistor. However, here you have another common gate stage. You have another common gate stage, and the voltage that we apply at this point, that voltage we have already found out is the voltage at the drain node of the M1 transistor. That voltage goes to the source of the M3 transistor. And you already know the equation for voltage gain for a common gate stage. You just apply that equation, which is Gm times Rd. So Gm of this transistor multiplied with Rd, the drain at the drain node, what is connected? You have R3 and you have a parallel path that goes to the gate of the M5 transistor, because again, the gate is impenetrable. So there cannot be any current going into the gate. So this is infinite resistance. You don't need to consider that. So the resistance at the drain terminal of M3 is R3. So that's so again, you can find out the gain of this stage and the voltage that is available at the gate of M5. So now M4 and M5 are both common source stages, right? Your source is grounded, input is applied at the gate, output is taken from the drain. They are both common source stages. Now for the common source stage, you know the voltage at the gate for both of them. You know the voltage at the source, so you know the VGS. And you also know what is the current that will be flowing at the drain terminal of these two. Because the drains are connected together, the currents will get added together. KCL. The currents will get added together, and then multiplying that current with the resistance connected at the drain, you'll get the final output voltage. Current multiplied with resistance gives you voltage. So that's what, like, just try to think about it logically. Like it may seem very complex, difficult problem at first, but just think about it logically. And just use 3 things. One is Ohm's law, one is KCL, one is KVL. That's it. You don't need to know anything else. You don't even need to know anything that you learned in this class if you know Ohm's law, KCL, and KVL. That's how simple it will become once you try to identify the different components of the system and try to logically relate them one after another. Now there is a PDF that I have uploaded that will help you with solving this kind of a problem. So let's go over that first before we discuss anything else. And I don't think we'll have time to discuss anything else today. So we'll start discussing that from Monday's lecture. So I have already uploaded this PDF in Canvas. So what you have is again a 2-stage amplifier. The first stage is a common gate stage. The second stage is a combination of this M2 and M3 transistor, which are both common source, and their drains are connected together. So it's very similar to the problem that you have in your homework 6, problem number 2. And the assumptions are also exactly the similar assumption. So for solution, stage 1, consider it as the CG, because first you have to identify it as CG. If you cannot identify it as a common gate stage, you'll not be able to make progress. So first, identify what each of these stages mean. That if your input is a source, if your output is a drain, only one terminal remains, that's your gate, that has to be your common terminal, so that is common gate. Input current is IN, output voltage is that IN current multiplied with R1, that gives you Vout1. Why all the current flowing into the output? Because there cannot be any current flowing down, all the current has to flow up because the resistance of IB1 is infinite. So that current is available at your output, that multiplied with the output resistance. What is the output resistance? You have R1, then you have this parallel path that goes to the gates of the M2 and M3 transistor. Because gate is impenetrable, you don't need to consider that. So the resistance is just R1, and the multiplication of current and resistance gives you voltage. Okay. So you can find out what is your the voltage that you're applying at the gate of the M2 and M3 transistor. That's this much amount of voltage. So at the final output, what you would have is basically you have to consider this stage 2, which are 2 parallel CS stages. So these are both common source stages, and their drains are connected together, so the current will get added up eventually. So the V for both the common source stages is I times R1, that is equal to Vout1. I out 2 for common source with M2 will be GM2 times gain, and I out 3 for the common source with M3 will be GM3 times gain. And both of them will have a negative sign because the voltage is common for both of them, and then your current will be in the same direction for both of them. So you just add those two currents up. At the gain of M2 and M3, I out 2 and I out 3 will be added up using KCL, and final output voltage will be addition of those two currents multiplied with the resistance that you see at the gain of these two transistors. And again, why you can do that? Because RO is infinite, so you don't even need to consider RO. So multiplying that resistance with the added up current, you get this final value, which is GM2 times GM3, multiplied with IN times R1 times R2. Now you can say that GM2 equal to GM3 equal to GM, and R1 equal to R2 equal to 1 upon GM. So just calculate that, you get this equation, and the gain is V out over IN, which will be just minus 2 over GM in this case. And notice that this is a TIA, the trans impedance amplifier. The unit for gain will be same as the unit for resistance. Why is this a trans impedance amplifier? Because your output is a voltage, input is a current. Voltage divided by current is an impedance or a resistance. So that's why it's a trans impedance, that you transfer current to a voltage. That is basically your transfer function becomes an impedance or a resistance. That's why it's called a TIA or a trans impedance amplifier. So we'll stop here and we'll start discussing about differential amplifiers in the next class. But hopefully this will help you solve your homework 6 problems by applying the idea of divide and conquer.